The last talk of the session is Alessandro Boselli from Marseille, the LAM. So he will talk about the relation between star formation and its surrounding environment.
Okay, thank you very much. So, the idea behind this project is that of understanding the process of star formation and the relation with the environment where star formation occurs at different scales, from, say, parsec scale up to megaparsec scale. And, star formation is one of the most important processes in galaxy evolution. So we know that the two star formation environment are tightly connected. For instance, the gas has to cool into giant molecular clouds where star formation occurs. This is on small scales. If you go to the scale of a galaxy, you know that the star formation occurs whenever the density, it's regulated by the density of the gas according to the Schmidt law. While if you go to higher scales, for instance, the cluster scales, you know that the activity of star formation of galaxies is perturbed by the surrounding environment. Gas can be stripped, removed. Gravitational perturbation can induce in fall into the nuclear region of galaxies, inducing the burst. And also the star formation itself can have an impact on the medium where it occurs via the feedback process. And this occurs from small scales of single stars inside H2 regions up to the starburst in dwarf galaxies, for instance, which is able to eject the gas and stop the activity. So the idea behind this project is that of taking some representative environments from the Milky Way star formation complex, in that case an image of a CU6, where whenever you do have multi-frequency observation, you can study the different properties of the gas, the different phases from the cold H1 and molecular gas to the ionized gas and hot gas, and the relation with star formation. You see, for instance, here in black dots are indicated the region where the H2 regions, and in color the different phases. From three phase is ionized gas and pHs, so dust. Where the density is high, you can induce a star formation process. The star within the H2 regions via wind compress the gas and expel the gas. This is also happening on the sides of the galaxy. If you look at the spiral galaxy here, NGC 628, you see that the star formation is located along the spiral arms, but you see bubbles whenever you have the resolution to do that. And that bubbles is because the star-forming complex is expelling gas at high velocity and pushing the gas away. You can induce a self-propagating star formation on this scale. And whenever you go to the clusters, so on a larger scale, you see that there are galaxies which are perturbed by the interaction. The first one on the top is a galaxy which is suffering ramp pressure while entering into the cluster. The gas is removed, the activity of star formation is quenched. We do also have gravitational perturbation where the gas can be stripped in some way, but also induced to fall into the center of the galaxy, inducing a triggering a starburst. And the distribution of star-forming regions in the small image, it's very asymmetric. It's because the gas is removed from some part of the disk, is compressed in other, so it's quenched somewhere and enhanced elsewhere. So the idea behind this project is to use the narrow band capabilities that are available at the CFHT with MegaCam. In particular, use the filter on the H-alpha line, which is the direct tracer of star formation, because it's due to the emission in the H-alpha is due to radiation of ionizing star, massive young stars. So with some condition, which are often satisfied, you can transform the flux, the luminosity in H-alpha into star formation rate. And also, it's a good tracer of ionized medium. So it's one phase which is particularly important if you want to study perturbations and if you want to see how the multi-phase medium is related to the process of star formation. So the idea is that of mapping different environments from star complex in the Milky Way, we can use this data to understand how the different phase of the gas, the atomic, molecular, ionized, the hot gas mixed with dust, interact in the process of star formation, how the cooling process proceeds with these regions, and also the feedback, how the stellar winds produced by young stars expel the gas, the Lyman continuum leakage, because the ionized radiation can come out from this region, which has an important implication also in studying the high redshift for the problems of ionization, for instance. For this, we could use, we propose to use narrowband imaging, particularly in the H-alpha band, but there are also two other filters, the O3 filters, which can be used to measure higher excitation energies, and the sulfur 2, which is in the H-alpha off-band filter at redshift 0. So that can be done. Well, a complex like that has a size you can see here on the plot of something like 20-25 square degrees. So we might map a few representative objects like that over 100 square degrees to have a statistical sample for this analysis. Well, the study of nearby galaxies has been already done, and there are two samples which are very good for this. One is the FANS sample, which include JWST, NEWS, HST, and ALMA data at good resolution, and the signal sample, which is being taken at CFHT with CTEL. So what we would like to do now is to go a bit further and study the cosmic web, nearby cosmic web, where we would like to sample on a statistical significant sample galaxies belonging to different regions from a high massive cluster like COMA 10 to the 15 down to groups and filaments. For this we need also H-alpha, but we'll use the H-alpha host filter, which we can sample, well, the Great Wall and the perceived species supercluster, which are visible. They fall at the right redshift for that, and they are visible in spring and fall time. Well, you see here the Great Wall, for instance. You see the filamentary structure there with clusters. The big one is COMA, and there are many groups and filaments. So we could select some given regions there. The small square is the field of view of megacam on the small right and on the left side. And we will benefit of a large synergy with other surveys to have a full set of multi-frequency data for the analysis. And finally, I have to say that whenever we do this kind of observation, we will get for free line emitters in the background, O3, O2, and Lyman alpha at the 3 different redshift. So we will be able to use this data to find the bright end of the luminosity function, the 2-point correlation function, clustering, but also study groups and filaments at this given redshift. So we can also study the evolution of the interaction of the star formation with the surrounding environment. This will come for free. We might need to have some pointed observation deeper to get to sample the intermediate luminosity function, the intermediate luminosities, and combine with deep observations with NEWS, for instance. Well, I just want to finish that the CFHT with megacam is very competitive because there are only 3 telescopes we have, which have these capabilities. Subaru, which is, well, an 8-meter class telescope, but only has a filter which is at Z0, so it's good for the Milky Way, but they do not have anything for something which is slightly at higher distance. And Blanco and VST in the south, well, within the south, we do not have much of this structure in that redshift range in the south. And, well, for instance, VST has a filter which is only at Z0. So for the Milky Way, has been designed to study the Milky Way, but not for this feature. So I finish here just showing you the image that Jean-Charles produced me. This, you see the two structures that we would like to analyze with these beautiful filaments, which are accessible. And so it means that we can observe during the whole year, and when we do not observe these filaments, we will observe the Milky Way, which is exactly when they are not visible. Thank you very much.
So questions? Thank you very much, Alessandro, for a very interesting presentation about star formation. I'm star people, like interested more in stars. Just remembering that some stars can be formed in galaxies when the dust will absorb all the visual light, so you will not see alpha emission. It can be just emission in infrared. So any idea how to combine your observations with radio astronomy to get?
Yeah, well, that's the dust attenuation is a key problem in determination of star formation in galaxies. But for instance, the fact that you have WISE data, you can combine it and the correct for dust attenuation. You can measure a global star formation rate for these galaxies. There are some recipes which work quite well and are available in the literature.
Okay, thank you. Other questions? I do have one for the environment studies. So how do you want to discriminate between the different cosmic web components? So filaments, groups, and it's not always obvious to do.
No, but you see them here, so that they are quite it's nearby universe, so the groups and the cluster are well studied and identified. So the idea is to map them up to, say, two virial radii, because there are some kind of perturbation which are acting in the center of the clusters and some in the periphery. So you should have a complete coverage. And filaments that you can measure with this the previous plot I've shown. This one you identify them using redshift, and you just have to select some of them. You cannot, of course, map everything there because it's wide range. You should select some representative regions and just map them. But are well identified. This is bit always been known since 30 years.
Other questions? No? So thanks, Alessandro.